cracking moment and safety of post-tensioned members. What will you take away from this presentation? Number one, what is the cause of cracking? Member safety at initiation of cracking, magnitude of the cracking moment, building code requirements for cracking moments, and design example. Now the figure shows a member at the top under bending, which is not cracked yet, and it shows below it when it is cracked. For low values of moment, the combination of compression and tension stresses of concrete shown in the figure at the top lead to a tension stress which is less than cracking, and the member will not crack. Now, increase in moment results in extreme fiber tensions here that reach cracking stress, and cracking initiates. Once cracking initiates, the loss of tension which was provided by the uncracked section results in drop in bending moment and reduction in the capacity. Added reinforcement across the crack provides the loss of moment capacity to resist the applied moment. So the bottom line is the amount of reinforcement which is available in the tension zone must be adequate to provide the tension necessary to resist collapse of the member. So in summary, what is causing cracking, and number two, what to do next, and also how the code is handling this. The questions is cracking of the section and safety of the member. At what value crack initiates and how much reinforcement you need, and also how the building codes handle this question. In addition, what is available in the literature in this respects. Now, this is the objective of this presentation. The primary objective of this presentation is to clearly define the magnitude of the cracking moment and the required strength subsequent to cracking and where this provision applies. But first, here at the bottom, first let us review the following simple example to better appreciate the phenomenon. The focus is on cracking and safety. Now, I go through this simple example because I note controversy among engineers as well as literature, and the objective of this simple example is to clarify or focus on where the controversy is and leave it to you to decide what you think is the right way to handle the situation. Now, for safety of a member, the resistance capacity of each of its sections must exceed the force demand that causes cracking. That is obvious, but let us follow it up. In this hanging member, I have the properties cross-sectional area. What causes cracking of this concrete? It has no reinforcement. And how much weight I have at the bottom, weight W. The bar has no reinforcement. The two questions I raise At what value of P will this bar crack? This gives the cracking force. Second question, once cracking initiates, how much reinforcement is required to be available in the section to avoid breaking of the member in two? This addresses the safety question. Both of these questions appear to be obvious, yet we go through it because it is not treated as obviously as it appears in the literature and in the codes. Now, the material of the bar cracks at 250 psi. Now, how much force is needed to initiate cracking? You take the cross-sectional area, 10 by 10 is the cross-sectional area, times the cracking stress, and that is the force. You need 25 kips in total to initiate cracking, 25 kips. Now, conclusion. The demand to cause cracking is the function of the member properties, not the magnitude of the applied force. Now, this is a very significant conclusion that appears very obvious. The magnitude of the force is not function of P, not function of the weight W. It is the function of geometry of the cross-section and its property. Now, this is obvious, but let us move ahead and see what comes next. So, question number 2. Once cracking is initiated, how much force do we need to be available to avoid breaking? Then, this covers the strength requirement. You would say, I have the cross-sectional area, I know what is the cracking strength, I know how much demand is, this is the demand force, so the demand is 12K. Therefore, the force W shall not be less than the strength. The strength shall not be less than the demand. So here we define a correlation between the required strength and the required demand. The required strength for safety in this example is less than the force that causes cracking. Now, remember, in this case, the required capacity happens to be less than demand. In this case, cracking does not result in the member, even though here, because we have a less demand less. That was a simple example. Now let us look at this one, which is a member post-tensioned, and it is continuous over a number of supports. And we have a section here, XX, and we want to look at what is happening at this section. In the general case, the compression P, this is a section XX. I have the section XX shown outside. There is post-tensioning through the section. On the right, I show the demand. Demand is axial force, shear, and moment M. The axial force P is related to compression, but is not necessarily equal to F. Why? Because there will be reactions at the supports. In the general case, the compression P acting on the section is not equal to the tendon force F. Why? Because in the general case, you have supports, and could be column, could be wall, and some of the force is taken by the walls and columns. The force P is in equilibrium with F plus reactions at the member's supports, along with other forces which could be here on the member and may have a horizontal component. Now, here I have reproduced the section. P is acting here. F is the force from post-tensioning. The actions on the member in the general case are shear, axial, moment. The axial and moment break down in these two. This is the stress distribution, consists of a precompression and a bending moment. The precompression, compression at center, is from the average force of post-tensioning. The geometry of the section and the resultant of the actions on this section are shown here. The compression force P and the member force M are the two items that control the initiation of cracking, compression and moment. The distribution of direct stresses on the section, direct stresses, I mean this distribution of direct stresses, are shown in here and broken down into their parts. So what would be the magnitude of this stress tension at the bottom? Tension at the bottom will result in cracking if its value exceeds the FCR. This is equal to this and this. So here I have a force due to bending moment, stress due to bending moment, and average precompression gives me the stress at extreme fiber, which can cause cracking. Here is the repetition of the same. The actions P, V, and M are resisted by the distribution of stresses on the cut section by this. These three actions are resisted by this distribution. Part 3 shows the distribution of stress on the face of the section from the combined actions of P and M. Cracking initiates when the extreme fiber stress of the member reaches the cracking stress FCR in this figure. Note that the stress at the centroid of the section remains P over A. This remains P over A. The distribution of stress on the section can be broken into these two components, can be broken into its originating parts, which are axial force and the moment shown here. Axial force and moment result in this distribution, which will in turn lead to the cracking stress. The extreme fiber stresses shown in part 4 add up to the cracking moment value shown in part 3. The sum of this and this add up to cracking stress. The moment causing this condition is the moment that initiates cracking on the section MCR, M cracking. Now, at this stage, you may wonder Why am I repeating myself? Dwelling at this simple diagram, the reason is obvious. For me, it's obvious because when you go to the literature, you see a different image and you get a different answer. That is the reason I'm repeating, to make sure that we are clear. Now, the cracking moment that initiates the extreme fiber tensile stress, this extreme fiber tensile stress, is given by stress from moment. This is a stress from moment plus stress from axial. So this is the cracking moment. 318 recommends the following for cracking moment stress. ACI says the cracking initiates when the stress reaches this magnitude in bending. Now, independent of that, this relationship which I have at the bottom right can be simplified to the relationship here on the bottom left, which says cracking moment is given by this value. This is the magnitude of cracking moment. A is the cross-sectional area, and S is the section modulus. I'm going to call this basic cracking moment expression to differentiate it with the alternative cracking moment. This is the basic, derived from this diagram. The alternative formula doesn't follow this diagram. Now, from the distribution shown, we get to this basic value. If you look in some of the literature, this is what you find. That in addition to what we have at the top here, it says the cracking moment includes the contribution of MPT. MPT is the moment from post-tensioning. Why and how, I am not sure what is the argument, but certainly doesn't look right to me. I think the one above makes sense, the basic makes sense. This is the basic relationship derived from this distribution. This is the alternative that you can find in the literature. For static indeterminate structures, the presence of hyperstatic reactions impacts MPT. Now, this expression that I have here expands on this. It says MPT, if at all were to be a consideration, must include the hyperstatic reactions, which again, if you look in the literature, it doesn't include the hyperstatic reaction. MPT that is given here is simply the force F times E. So, as far as we are concerned, this is the right formula at the very top. What about building codes? Building codes have this provision to avoid failure of a section at initiation of cracking. The reinforcement in the section must develop moment capacity not less than the cracking that initiates the crack. That looks very reasonable. The cracking moment requirement requires a safety factor, K, the safety factor K. In other words, a section which has a capacity, as far as ACI is concerned, 1.2 times the cracking moment is considered safe. Now, ACI permits you to waive this requirement. I have it somewhere down in the following slides, but the penalty is very high. Now, this is the relationship for ACI. The capacity should be 1.2 times the cracking moment, or the other provision, which I'm going to come up with the following slides. Phi is the strength reduction factor. EC2, the European code, has a safety factor of 1.15. The section at initiation of cracking of beams reinforced with unbonded tendons. That's very interesting. That European code states that this requirement applies to unbonded tendons that are applies to beams that are reinforced with unbonded tendons. But EC2 permits the requirement to be waived if the strength of the cracked section is not less than the force demand. That's very interesting. Very interesting. Why? Let me repeat it. EC2 says if subsequent to cracking, the strength of the section is not less than the demand, you can waive this requirement. My response to this is, at design time for safety, a requirement is that all along the member you have safe design. You have capacity in excess of demand. In other words, before you get to the question of checking cracking, you have already satisfied the requirement of safety along the entire member. So this is really redundant. Nonetheless, it is in the code. ACI 318, in its latest, requires the evaluation for slabs with bonded tendons. EC2 has the opposite, with unbonded, for both one-way and two-way systems, but also requires the application to beams reinforced with bonded tendons. ACI wants to penalize the application of bonding tendons. Now this is interesting. The latest ACI 318 permits this requirement to be waived, provided subsequent to cracking, the section's capacity is not less than twice the force demand. Now, that is very vague. That is in later ACIs. You can forget about this factor of safety if at the location of crack, the capacity is twice of demand. Now, what is the demand? Is it 1.2 dead, 1.6 live, 1 hyperstatic load combination? Is that the demand? It is not very clear. Or is it dead, live, and hyperstatic? Now, that is left to the judgment of the engineer. Now, slab constructed with unbonded tendons, neither ACI nor AC2 require check for initiation of cracking. In one of the following pages, I will explain why. Just pay attention here that neither of the two for this configuration require checking for cracking. Now for unbonded, ACI requires checking for safety after cracking. So the fact that EC2 requires checking for the left. ACI requires checking for the right. To me, implies that none of the two are fully clear. What is the consequence of cracking and where it should apply? You would not expect such a diverse opinion in the two cases. I have in the image at the top the distribution of stress, when extreme fiber stress over a design strip of a column-supported slab. Here, the maximum stress at local stress is shown there. If cracking occurs, and this is stress for cracking, there is room on the left and right for the stress to redistribute and develop capacity. So it appears that for column-supported slabs, the initiation of cracking at near the column, that's where the maximum stress is not going to be very critical. So evaluation of the cracking moment is not required in ACI for slabs reinforced with unbonded tendons. The loss of, okay, this is what I explained. Local increase in strain. Local increase in strain at the crack location will be distributed over a length of slab crossing the crack. This does not apply to beams or one-way slabs where the stress is all uniform at the top. You do not have the reserve that you have here. Due to redistribution, formation of crack at a point does not necessarily lead to loss of strength capacity. Now let us go over a design example to see how it all applies. Here I have a beam with post-tensioning and I want to know, and rebar, I want to check it for the compliance at initiation of cracking. At midspan, I want to check it, and at quarter span, at midspan and a quarter span, and here are the particulars of the section. In what follows, the reinforcement is added to develop capacity in excess of cracking moment or equal to cracking moment. In each case, calculate the reinforcement, if any, to meet the safety requirements of the code. The geometry is as shown. This is the concrete strength. The cracking stress is this much as given in ACI, and I have 6 half-inch strands at the through the member following a parabola. Effective stress is also given. These are the parameters which enable you to calculate the demand and the stressing. Good. Let's calculate the cracking moment. This is the cross-sectional area of each strand. Total post-tensioning is given by this value. Area of the section is this. Average pre-compression is the total post-tensioning here. Total post-tensioning divided by area is this. Section modulus is this. Cracking stress given. Yield stress is 60 because that is what we will be needing when it comes to addition of reinforcement. Now, using the basic expression, which is this, the cracking moment is calculated to be this value for midspan. Now, using the alternative expression, the crack, which is this, the cracking moment includes this MPT in it, MPT, and its magnitude is the 458, 324. Obviously, it has a much higher moment because of inclusion of MPT. So there is a significant change between the two. When it comes to code compliance, we check it now at the quarter span here. That was the other requirement. At quarter span, or everywhere, the moment capacity of this section is calculated. The moment capacity is then compared with demand arrived from the cracking moment. Reinforcement is added where capacity falls short of demand. This is the procedure. And at midspan, this is the moment capacity. I've used this formula. From the basic expression, this is the moment capacity. This is, so to say, a conservative, easy way to find the moment capacity of a post-tensioned member. I have in another presentation a greater description how to simply arrive at this simplified expression. From alternative, this is the cracking moment, and the moment capacity calculated here as bottom left in each instance exceeds the demand, so we are in good shape. We don't have to do anything at midspan for this example, irrespective of what we use. Now we go to quarter span. At quarter span, MPT will be the post-tensioning times its eccentricity. So the moment capacity will be calculated, and this is the amount. I have calculated the eccentricity here at the quarter point, assuming simple parabola. From basic impression, the value is this. Cracking moment is the same. No rebar is required because the moment capacity is more than demand. This is the demand. The alternative expression has this P times E added to it. It says rebar has to be added because the moment capacity falls short of 1.15 of the demand. Now, in summary, I have this diagram. In this diagram, this is the moment demand. This is the cracking moment based on basic expression. And this is the cracking moment, the dotted line, based on modified or alternative. And here is the capacity. Capacity, as you notice, is up from here to here, is larger than either of the two. From here to here, capacity is more than either of the two requirements, so no rebar is required. From here to the support, depending on whether you use the alternative or you use the basic, you fall short of demand. One of them, which is the alternative, requires rebar here. The basic requires rebar there. This is if you want to follow the cracking moment requirement. This doesn't make sense because you normally don't put reinforcement here. This is where you put reinforcement. But if you want to go through the code compliance, this is what you will end up with, unless you go through the loop of showing. If you want to go through the ACI loop, you have to show that at these locations, at this location, the capacity is twice the demand. And if you go to alternative, the literature, this is where you have to go calculate the capacity. So it also shows that the cracking moment of the section using the base expression and the alternative expression shown here. This is the diagram. The moment capacity of a post-tensioned member varies along its length because of the change of tendon profile. Reinforcement is added where capacity falls short of demand. Now, inclusion of post-tensioning moment in cracking moment values leads to added reinforcement where it is neither needed nor provided in the common design. In the common design, engineers don't put this. The code stipulation of cracking moment needs to be modified to address clear definition of the value of cracking moment and where the cracking moment consideration applies. These two are really not fully clear. So the recommendation, as far as I'm concerned, is the following. Value of cracking moment is this. Use this as far as I'm concerned. The cracking moment check should be limited to a section that is not reinforced to meet the strength requirements of design from application of load. Where is that section? I don't know, because by the time, you see, you do serviceability check, and then you do safety check. And this is part of your safety check. And the first step in safety check is that you calculate demand and you make sure that everywhere the demand is met by adequate capacity. So this location doesn't exist anyway. In reinforced concrete, design the reinforcement for strength. The design reinforcement for strength is based on ductile response of concrete and post-tensioning. I want to say here that even if you have a demand which exceeds the capacity, in reinforced concrete, you use redistribution. You have the option of redistribution. This is just extra, I would say, safety. Development of cracking in resisting the applied load is implicit in common design methodology. What I'm saying here is that the way you do your design, it is based on post-cracking, not pre-cracking. So the question of initiation of cracking shouldn't come up. Why? Because the entire design that we do is based on post-cracking behavior of concrete, ductility of concrete. So the required reinforcement shown in A is triggered by the requirement of cracking moment. Anyway, summary. I started by trying to explain bring an understanding of the cracking moment, relationship between safety of the member and initiation of crack, magnitude of cracking moment. Cracking moment is a function of geometry, I emphasize, and axial force and the cracking stress. Basic cracking moment expression is something which I emphasized, and I also gave here the alternative cracking moment expression, which is in some of the literature. Neither ACI nor EC2 give you the expression. So it is left to you to decide what is the valid expression. It is recommended to apply the requirements to locations where the section is not designed to meet the safety requirements of the applicable code. There is no such location because the codes require that the entire length of the member should be safe, not selective locations, but nonetheless, this is in the code anyway. That brings me to the end of the presentation. The material that I presented to you was extracted from this book, and I thank you for your attention.